Chem. Today we're going over section 10.2 on CK12, which involves empirical formula. So empirical formulas and molecular formulas, we use data from percent composition to determine these two things, which is why we did that first. So it's really related to percent composition, but it's also kind of like a new topic. So the first thing I want to talk about is what is empirical formula. We've heard the terms molecular formula before, or chemical formula, but we haven't really talked about empirical formula. So empirical formula is a formula that shows the lowest whole number ratio of elements in a compound. This is also the lowest whole number ratio of the subscripts. Because ionic compounds are a three-dimensional network of positive and negative ions, all formulas for ionic compounds are inherently empirical. So ionic compounds always have the lowest whole number ratio. We find those formulas by doing the crisscross to cancel out charges for ionic compounds. So we reduce to find those compounds already. So for ionic compounds, which remember their molecular formula is called a formula unit, is already equal to the empirical formula. For molecular compounds, which are two nonmetals together in a compound, this may or may not be true. So sometimes the empirical formula is going to be equal to the molecular formula, but sometimes it's not. The molecular formula can be reduced to find the empirical formula. So we're going to look at examples so that you kind of know what this looks like. So the first one we're going to talk about is H2O, water. H2O is a molecular compound. Hydrogen and oxygen are both nonmetals. The subscripts of H2O are already present in the lowest whole number ratio. We can't reduce any further. So the empirical formula for H2O is H2O. The empirical and molecular formulas are equal to each other. But for ethene, C2H4, this is not true. We can reduce C2H4 to a lower whole number ratio because both numbers are divisible by 2. So if we divide 2 by 2, we get 1. If we divide 4 by 2, we get 2. So the empirical formula for C2H4 is CH2. The ratio of carbon to hydrogen in ethene is 1 to 2. So that means that if we are considering one molecule of ethene, the ratio is 1 carbon atom to every 2 hydrogen atoms. If we're considering 1 mole of ethene, the ratio is 1 mole of carbon atoms for every 2 moles of hydrogen atoms, or 2 moles of hydrogen. So the subscripts of formula represent the mole ratios of elements in that formula, as well as the atomic ratio. The thing about empirical formulas is they are not unique to compounds. So two different compounds can have the same empirical formula. Because empirical formulas are the lowest whole number ratio, multiple compounds can have the same empirical formula or the same ratio of elements in a compound. So ethene shares an empirical formula of CH2 with multiple things: C4H8, C6H12, CH2, C7H14. All of those compounds have a carbon to hydrogen ratio of 1 to 2. Because of this, compounds can only be identified through their molecular formula, and we're going to learn how to find that later in the next section. So this section we're going to focus on how to find the empirical formula. So again, looking at these examples, if we reduce them to the lowest whole number ratio, 4 and 8 goes to 1 and 2, 6 and 12 goes to C1H2, CH2 is already reduced to C1H2, and C7H14 reduces to 1 to 2. So all of these compounds share an empirical formula with ethene, C2H4. In the actual chemistry field, like in laboratories and different studies, chemists can use elemental analysis to determine the percentage of each element contained within it. So this pops out as a percentage, which is what we've been working to find. These percentages can be transformed into mole ratios of the elements, which leads to the empirical formula. So these are the steps we're going to use to find the empirical formula given percents. First step, we assume that we have a 100-gram sample of the compound so that the given percentages can be directly converted into grams, okay? So technically you could assume any sample size. So remember, no matter what your sample size is, that percentage remains true. If you have 1 atom, that percentage is true. If you have a whole truckload of that sample, that percent remains true. By assuming 100 grams, we don't really have to do any fancy math or anything like that. So let's say I have an element that they tell me is 50% of the compound. I convert that 50% and say 50 grams, okay? Because remember, percents are expressed out of 100, so if we assume 100 grams, it just goes from percent to grams. Really easy. Second step, we use each element's molar mass from the periodic table to convert grams of each element into moles of the element. So remember to go from grams to moles if you consider your roadmap. What we're going to do is divide by the molar mass, which is the same thing as taking grams times 1 mole divided by molar mass. So the grams would end up canceling out, and that tells us moles of the element. In order to find a whole number ratio, we divide the moles of each element by whichever of the moles from step 2 is the smallest. And we'll go through an example that kind of shows this as well. But if we pop out, we have an element with 3, or a compound with 3 elements, and we get 0.1, 0.2, and 0.3 moles for those 3 samples, we divide all of those things by 0.1 because it is the smallest number. For number 4, if all the moles at this point after we divide are whole numbers or really close due to rounding, the empirical formula can be written with the moles as a subscript of each element. Okay, so once we divide, if all of those are whole numbers, we use those for the subscripts of the empirical formula. Number 5, we only do if this is not true, if we don't have nice whole numbers. So in some cases, 1 or more moles calculated in step 3 will not be whole numbers. If that's the case, we multiply each of the moles by the smallest whole number that will convert into a whole number, write the empirical formula. So an example of that that's really wordy and weird is if in step 3 we divide and get 1.5. 1.5 is not close enough to 2 to round up to 2. We only round up to 2 if it's like 0.9, okay? So 1.5, what do we do to get a whole number? Anything that ends in 0.5, we will multiply by 2, because 0.5 is equal to a half, 1 over 2. So if we multiply by 2, we'll get a whole number. So if anything ends in 0.5 in those 3 samples that we get, we multiply all of those numbers by 2 to get our lowest whole number ratio. So let's consider, we will consider some examples. There is a little empirical formula rhyme to help you remember those 5 steps, and it's, oh my goodness, oh no, there we go. Percent to mass, mass to mole, divide by small, times to whole. Okay, so percent to mass, assume 100 grams of the sample to go from percent to mass. Mass to mole, using molar mass from the periodic table. Divide by small, the smallest number that you get from that mass to mole answer, and times to whole. That times to whole is the step number 5 if you do not get whole numbers from dividing by the smallest. So we can consider some examples. Let's say we have a compound of iron and oxygen, 2 elements. We analyze it and find that it contains 69.94% iron and 30.06% oxygen. We want to find the empirical formula of the compound. First step, we're going to list the knowns and unknowns. So we know that we have 69.94% of iron and 30.06% of oxygen. The empirical formula we're looking for is going to be Fe with a subscript and O with a subscript. Next, we're going to calculate using that little rhyme. So percent to mass, we're going to assume 100 grams of the sample. So we are going to assume that 69.94% of iron with a 100 gram sample, that would be 69.94 grams. For oxygen, same thing, 30.06 of 100 would be 30.06 grams. Next, we're going to go from mass to mole, so convert grams to moles using the dimensional analysis. So for iron, we have 69.94 grams over 1. We're going to multiply that by 1 mole over the molar mass of iron, which is 55.85 grams, and we get 1.252 moles of iron. For oxygen, we have 30.06 grams over 1. We're going to multiply that by 1 mole over 16 grams, which is the molar mass of oxygen, and we get 1.879 moles of oxygen. Next, we're going to divide by small. So the smallest of the two numbers was from iron. 1.252 is less than 1.879. So we're going to divide both samples by 1.252. When we do that for oxygen, we get 1.5 moles of oxygen. And when we do it for iron, we get 1.0 moles of iron. So here, iron has a nice whole number, but oxygen does not. It is not 1.9, we can't round up to 2. What are we going to do? We're going to multiply both of these things by 2 to get rid of that weird 0.5 decimal. So 1.5 times 2 is going to be equal to 3, and then 1 times 2 is going to be 2 for iron. So oxygen and iron have a molar ratio of 3 to 2 in the compound, so the empirical formula is going to be Fe2O3. So for review of this section, what is an empirical formula? What does it tell you? But also, number 2, what does it not tell you? Or sorry, number 3, I just read through all of those. So what is an empirical formula? What does it describe? How do we find it? 2, what does it tell you? Okay, it tells you one really nice thing, but for number 3, it doesn't tell you another really important thing, okay? So let me know if you have any questions. That's it for the section 10.12 notes.